Hello, Namaskar. How are you? We will take today integrated rate equation. Okay. So what is integrated rate equation actually? In the previous videos we have discussed differential rate equation, and from the differential rate equation what we calculate the instantaneous rate and then rate constant as well. So in instantaneous rate we take a small change in concentration and small time interval, and that is not always convenient, okay, to calculate the rate law, to calculate rate constant on the basis of instantaneous rate. It's little bit challenging work because we are taking a small part of reaction, okay. So if we take the big time interval overall reaction, that is called integrated, okay. Integrated means it is including the whole reaction, okay, from this time to that time. So that is why it is not always convenient to determine the rate constant and rate of reaction from the differential rate equation, and hence the differential rate equation is integrated, and then we determine rate of reaction. It is helpful in calculating the time in which the reaction is like 25% completed, 50% completed, or 99% completed. So from integrated rate equation it will be easy to calculate the time taken in such type of manner, okay. So we will take zero order reaction and first order reaction, and we will integrate the differential equation, and then we will see how the rate constant is calculated from this integration, okay. So first we will take zero order reaction, and we know that zero order reaction is a reaction in which the rate of reaction is independent of independent of concentration of reactant, am I right? Or in which the rate of reaction will not vary with change in concentration of reactant, am I right? So, or what we can say, the rate is proportional to zero power of the concentration of reactant. So that is what is called a zero order reaction. Let us take a reaction in which the reactant R is converting into product, and suppose it is a zero order reaction. So at time t0, when the reaction did not start, at that time the concentration was R0, initial concentration was R0, and of course product was 0, am I right? Then at t time the concentration of reactant becomes R. So the concentration of product will become R0 minus R, am I right? Because this much concentration has changed into product, and that is suppose X. R0 minus R is equal to X. Now for this reaction, the differential rate equation we can write like this: minus dr upon dt is equal to k0 r raised power 0, okay, because zero order reaction is what we are discussing here. So power 0 means it will become 1. So what will be then? Minus dr upon dt is equal to k0. K0 is rate constant for zero order reaction. So this is the differential rate equation, what we have already discussed even when we discussed rate of reaction, instantaneous rate of reaction, okay. So now what we have to do is integrating this equation number 1. Suppose this is equation number 1. So if we will integrate this equation, then we will get like this, okay. Integration of dr is equal to minus k0 integration of dt, and that will be equal to r is equal to minus k0t plus I, where I is an integration constant. I is what? The integration constant, and the value of I can be calculated on the basis of conditions. And which are those conditions? Suppose t is equal to 0, it means reaction did not start. Okay. So then R will be equal to R naught, of course the initial concentration of reactant, and in that situation according to equation number 2, I will be equal to R naught. Okay, because K0 T will become 0 and R will become R naught like this. So I is equal to R naught if we are putting these conditions. This is equation number 3. Now putting value of I from equation 3 into equation number 2, what we will get then, R will be equal to minus K0 T plus R naught. Okay, and this is an equation which seems like straight line equation. Straight line equation is what? That is y is equal to mx plus c. Okay, where is the variable which we are taking on y axis, m is constant, x is what we are taking on x axis, and c is intercept. Okay, this one we will see intercept. So this equation is like this straight line equation, and from this what we can get is R naught minus R. Okay, R naught minus R is what? The concentration of product, that is X, okay, at time T, or if we want to calculate K0, that will be equal to R naught minus R upon T. From this equation we can calculate rate constant as well as the time taken. Okay, so it's quite easy. That is why we have integrated the differential rate equation. So from this straight line equation, if we extra plot a graph between concentration, that is y is what here? R, concentration over y axis, and mx, m means k naught here, k0, okay, and x means t, time we are taking on x axis, so that is x, and plus c, that is intercept, this one. Okay, so if we extra plot a graph between r and time, then we will get the slope like this, that is negative slope. Why negative slope? Because we can see here minus k0 t. Am I right? So this is the concentration, initial concentration of a reactant. Am I right? And that is equal to R naught, and that is equal to intercept. It means this one, intercept will be equal to the initial concentration here in this graph, and the slope, that is tangent, that will be equal to minus k. Okay, p by b, perpendicular upon base, so that will be equal to the slope. So by using this slope we can determine the value of k0. Am I right? So this is how the integrated rate equation is discussed, and it's convenient to determine the time from here, from this equation, because if we are knowing the concentration at time t for reactant R naught we are already knowing, and we are knowing the rate constant k0, then we can determine what t, time taken. Okay, means 25 or 25%, or 25% means what? If we are saying that reaction is 25% completed, it means R naught is 100. Okay, 25% completed means R will be 75. Out of 100, 25 is completed. So R is what? Concentration of reactant at time t. So that will be 75. T we have to calculate. Okay, and K0. We know that K0 for zero order reaction, it will be given to you, and hence we can calculate the time taken for 25% completion. Alright. So this is convenient to calculate, and if we are knowing the time, then we can calculate rate constant as well. Alright. So this is how we discuss the zero order reaction and its integrated rate equation. Zero order reactions are however uncommon, you know, but occur under special conditions. Most of the catalytic reactions, okay, catalytic reactions means these heterogeneous catalysis, especially the reactions which takes place on metal surface, and metal is used as a catalyst. So that is heterogeneous catalysis. So these are heterogeneous catalysis reaction which follow zero order kinetics. Okay. Enzyme catalysis. Okay. In our body there are a lot of reactions happening, and these reactions are enzyme catalyzed, and reactions on some metal surface are few examples of zero order reaction. If we can exemplify, like if we are taking ammonia, okay, ammonia on platinum surface, then that reaction follow a zero order reaction. If we are taking ammonia and we are heating it around 1180 degree, or yes, 1130 degree, 1130 Kelvin, platinum is used as a catalyst, then it will break N2 plus H2. Okay, you can balance it. So this reaction is happening on platinum surface, heterogeneous catalysis, because ammonia is gas, these are also gas, so heterogeneous catalysis. Okay. Follow zero order reaction. Likewise, if we are heating hydrogen iodide, and it will break up, okay, into H2 plus I2. So this is also an example of zero order reaction. Some of example we should know which follow zero order kinetics. Okay. So when we see the catalytic, like catalytic hydrogenation also follow sometimes zero order reaction. So this is how we can calculate the time taken, as well as we can calculate the rate constant on the basis of integrated rate equation for zero order reaction. Okay. Another term which is important for kinetics of a reaction is half-life. What? A half-life of a reaction. Half-life means what? Half-life means the time in which a reaction completes 50%. If a reaction is 50% completed, and if we know that time, so that time will be half-life of that reaction. Okay. So half-life means the time taken to complete the reaction 50%. Okay, means 50% reactant if converted into the product, then what we say, the reaction is the time taken is half-life of that reaction. Okay. Like for zero order reaction, if we want to calculate the half-life, okay, so how can be calculated that half-life? If we want to calculate, say, K0 for that reaction, for zero order reaction, if we are saying, then what will be the situation at time t will be equal to t half 50%. Am I right? Then what will be the case? R will be equal to R naught upon 2, means 50% of reactant left and 50% of reactant converted into product. So that time will be t half-life of that reaction. Am I right? So if we put this value in this equation, suppose it is number 5 equation, then what we will get is K0. Okay, K0 will be equal to R naught minus R naught upon 2, and T will be equal to T half. Okay, 50%. Okay, T will be equal to T half. So this will be the situation. This will be equal to what? R minus R naught half will be equal to R naught by 2. Am I right? And T half, T1 by 2 is equal to K, or what we can say, T half of a zero order reaction will be equal to R naught upon 2K0. T half of a zero order reaction will be equal to R naught upon 2K0. It means what? This is constant, this is also constant. So what we can say, T half of a zero order reaction is directly proportional to R naught. It means the the T half of a zero order reaction is directly proportional to initial concentration of a reactant. Am I right? T half of a zero order reaction is directly proportional to initial concentration of a reactant. So this is how we can calculate T half, because T half is an important term which is used and which is asked in so many examinations, including your board exam. So that we will calculate for both zero order as well as for first order reaction, and that can be calculated from the solution of integrated rate equation. Okay. T half is what? Again I will be repeating, the time taken in 50% completion of a reaction is called its T half. Okay. So this is T half of a zero order reaction. It is clear from the equation that T half for zero order reaction is directly, that is what is written here as well, we have discussed. Okay. So T half and integrated rate equation was what we have discussed in this lecture. So keep studying, be happy, and minimize the use of plastic. Happy chemistry. Thank you very much.